This is an overview of GNURadio's file metasync block. We're going to talk about the whys. Why would you use it? We'll look at some key points in the documentation, and then we're going to show a demo of recording a file and then analyzing the file. So why would you use it? Normally in GNURadio, we're really interested in the streaming data generated by a device such as a software-defined radio or an internal block in GNURadio. To be able to use that data, we really need to know some of the metadata properties, such as the sample rate, what the data type is. If it's a software-defined radio, what's its center frequency or its amplifier settings. And the file metasync block gives us a convenient way to save all of that information in a single file. Additionally, one of the other highlights of the block is that if you're doing processing on the data and you're generating events, such as if there was a detection of binary data, you can include that in this file so that you know what was found in the data if you want to compare it against, let's say, some other demodulation algorithm. So let's now highlight some key points in the documentation. So we're now looking at GNURadio's documentation on the file metasync block, and the documentation can be found at this site, and I'll include that in the notes. So the documentation is divided into an overview of what the block does, and then also some of the key metadata elements that are included in the file, and then also the parameters that you can configure this block with, and we'll go over that in the demo. And then it shows an example flow graph, and we'll actually run this flow graph in the demo. Finally, there's the source code files, which are really useful if you need to have questions about the specifics, and a FAQ, which answers some questions about how the data is organized and then how to read the data. So the file metasync block can generate two different types of data files. It can either generate a data file where you have both your streaming waveform data in the file along with all the metadata such as sample rate and center frequency and if events occur. So in this case we have some block that was analyzing this data and then in real time generating zero crossings and peak detections, and if you were wanting to save that information, the file metasync block will save those stream tags in here. So this is all in one file where you have both all of the waveform data and the header data, which includes both the metadata of the sample rates and then also any tags. Another way for the file metasync block to generate data is known as detached headers, and in this case this looks more like a traditional data file where you have just the waveform data in one file and then the metadata in another. Now if you're just given this file here, there's no way you can determine, you don't know what the sample rate is or any of the other features unless you also have this file. So this is handy if you have some traditional systems that can't read the file metadata format, so that you can then feed in this file into it, and then you would somehow load this information, either parse it and then provide that information to whatever processing code that you have. And in this case, one other point to highlight is that whenever there's a new stream tag, a new data segment is generated. So in those data segments always have a header and then along with the metadata and then a single stream tag. And you can also set the file metasync block to generate new headers after a certain amount of data. So in this case there was no stream tag, but because the segment got long enough that it simply generated a new header. In this case, you have the exact same, all the same number of headers here, but they're all just stacked consecutively in a single file. So now let's look at how we would actually run the block and look at the data. So this is the flowchart that was used in the documentation, and it's divided into several parts. First, we have our signal source, which is just a sawtooth waveform generated at 100 Hertz. And we're going to create tags, stream tags, every 320 samples, and that's just taking the sample rate, which is 32 kilohertz, and then dividing it by 100. So every 320 samples, basically at the start and at the every cycle of this sawtooth will get a new stream tag. We then take those tags and bind them to the data of the sawtooth and then save it with the file metasync block. Now the data that's being saved in the tag, it's a key value pair, and the key is a strobe, and so this in turn just means to take this string value and convert it to a format that's used by the PMT library, and then the strobe value is going to be converted also to that same value or string value. And so that strobe value comes from this GUI where we're basically saving what either option are. So either the 0 or the 1 will be recorded to the file depending on what we've selected. The file metasync block, we specify our location of where we want to save the block, our input type, which will be floating point, the same as all these data types, the same as your stream data. And then this is the max segment size. This is the size to generate a new header whether or not there were stream tags. So every time there's a stream tag, it'll generate a new header, but this will also generate a new header every certain number of samples. And we can either create a detached header, so that's the 2-file setup. If we have this on, we have it off, so it'll be just a single file. Now this extra dictionary is where we can embed additional metadata into all of the blocks, so all of the data segments. And in this case, we're simply just going to include the key value pair of initial and then the numbers 3. And this information is useful. So this could be something like center frequency or some data that wouldn't change throughout the file. So if we then run the block, so we run the block, we see the GUI pops up, and we can just close it, whichever file generated. We can now go to our Jupyter Notebook, and with our Jupyter Notebook, we'll look at the code to load the block, and that's given here. And so in this case, what we are doing, we're importing some blocks from some modules from GNURadio, mainly these and this, to be able to manipulate the file. Here's our file that we saved. So what we do is we open the file and then we read, and in this case we're reading 3 data segments. So it loops through for each data segment. What it does is you read that header in front, and then you have to deserialize it, and then you parse the header. And so we'll see the output of that parsed header. So that includes things like the number of samples and specific metadata. Now this extra length is the data that we put, that initial 3 that we had put in the metadata block. And then we read, if there's additional data, we can read that out of the header. And finally, we read the actual data from the file, which is given by the number of items in the header and then what the data type is. So it's not n items isn't the number of bytes, but it's the number of items of a given data type, in this case float 32. And then we'll read that data and we'll display that data. So first let's read 3 blocks and take a look at this, and this matches up with what's in the FAQ of the documentation. And so we can see that some of this header information that's included are things like the sample rate that we have, the location, the number of the item size in bytes, so it's a float 32, so it's 4 bytes, and the data type and whether it's complex data, and this is the length of that header. We also include that extra length, and this is what we had specified in the metadata block. And then these are the number of data elements read, and so 320, and that's because we're generating a stream tag every 320 samples. And so this initial one, you don't see the stream tag because you see that marks the beginning of the next block, and so that's that strobe 0 right here. But we have the initial 3, so we have this initial 3 for each of the blocks. And so if you look at these 3 blocks, the initial 3 is the same, and then we get the strobe tag every 320 samples. Now if we want to look at the data, we can then take that, which would be from the last segment of what we converted, and we converted it to a NumPy array. And then we can just take this, and using matplotlib, since it's a NumPy array, we can just plot this. I'm showing both the real and imaginary in case it was complex, but you shouldn't see anything there. And of course, for the imaginary part, we don't see anything. But we see then our sawtooth waveform. One of the other interesting points is if you want to make your own dictionary, we used for the extra dictionary, you could either have it blank, which would be this line, or you could set it to a single key value pair, which is what we did right here. If you want to use additional key value pairs, you just keep adding the key value pairs. So this concludes the overview of the file metasync block. I encourage everybody to look at the documentation in detail, especially the source code. I think it's really well written and a great way to see what some of the finer points of what's going on. And if you think of improvements for either the documentation or features, it'd be great to get involved with the GNURadio project and contribute.